Hi, I am Uriel Lopez Herrera and I will present my poster titled Influence of Calcium Oxide on Structural, Chemical, Optical and Luminescent Properties of Dysprosio-doped silica glasses. In Mexico, the burn of fossil fuels for generation of electricity, together with the need to illuminate more homes and public areas, have contributed to environment pollution. In this way, if more efficient light systems are used, these consumptions can be reduced. LEDs are the most efficient light system with cool light emission, lower energy consumption and less energy loss in the form of heat. However, they have some disadvantages, such as low chemical and thermal stability and polymeric degradation. In this manner, an alternative material that can improve this light system are silicate glasses, doped with dysprosium, since they have good physical and chemical properties, such as they are polymer-free, great thermal and chemical stability, and they can emit white light. In this work, the synthesis was carried out using the melting quenching technique. In the process, precursors were placed in a platinum crucible and melted at 1500 degrees for 2 hours. The melting samples were quenched a preheated stainless steel plate at 450 degrees, with subsequent cooling at room temperature. In the diffractograms, no characteristic diffraction peaks of crystalline materials were found, verifying that all samples are in amorphous state. In the FETIR, the increase the calcium oxide concentration in the glass, the breaking of the bridging oxygen bonds is promoted, generating a greater amount of non-bridging oxygen and increase the vitrification in the vitreous network. This can see in the deconvolution of the FETIR spectrum, where in the sample SA and SB decrease is observed in the red signal of bridging oxide, and in the sample SC and SD the red signal disappears and the brown signal appears. Therefore, the addition of calcium oxide in the vitreous network can generate the vitrification. In the UV spectrum, 6 energy levels were found corresponding to the electronic transition of the dopant ion dysprosium. In this, it was observed the calcium oxide concentration increase, all energy levels increase, but specifically 6p 7 because it's the most intensive. They become the most suitable to excitate doped glasses. The optical band gap decreased from 4 to 395, and the disorder in the glass structure increased with the addition of calcium oxide. In the photoluminescent spectra, it is observed 4 well-defined peaks. The first corresponds to blue transition, the second to yellow transition, and the 3 and the E and the 4 to red transition. The increase in the calcium oxide concentration shows that the second peak, yellow, is the most influenced, with the SD sample being the one with the highest intensity. On the other hand, it is observed that the sample with the lowest luminescent intensity correspond to the glass with the 4% of the dopant. With reducing the doping, the luminescence increase until reaching a maximum values for the sample with that 25%. In the calculation of CA, it is observed that samples for that 10 and 1 have a very similar shade of yellow. But by increasing the dopant concentration by 2, 3, and 4% more, the yellow hues shift toward the white area. This result helps to use verify that phosphor with white light emission can be obtained if the amount of dopant modifier. In conclusions, the FTIR and XPS results indicate that the addition of the calcium oxide promotes the formation of the non-bridging oxygen in the glass structures. Consequently, the addition of the calcium oxide enhances the luminescence due to the higher incorporation of the dispersion ions in the glass interstitials, and the CA chromaticity indicates that the possibility of obtained white emission in silicate glasses doped with high concentration of dysprosium.